In this example, let's find the general solution of the linear system of differential equations given by y prime equals 3, -6, -3, 0 times y, where y is the vector function xy. We start by finding the eigenvalues lambda 1 and lambda 2 as roots of the characteristic equation. 0 equals the determinant of 3 minus lambda, -6, -3, 0 minus lambda, which multiplies out to lambda squared minus 3 lambda minus 18. Factoring this quadratic as lambda plus 3 times lambda minus 6, we get the values lambda 1 equals -3 and lambda 2 equals 6. Now for each of these eigenvalues, we need to compute the eigenvector. For lambda 1 equals -3, we need an eigenvector v1 equals ab, so that a times v is equal to -3 times v. That is, 3, -6, -3, 0 times our unknown vector ab is equal to our eigenvalue -3 times that unknown vector ab. To figure out a relationship between a and b, we'll want to multiply out both sides. On the right-hand side, we can multiply that scalar in and have -3a, -3b. On the left-hand side, we'll need to do our matrix multiplication, so we'll do the dot product between the top row of a and our column vector v. That is, we'll have 3 times a minus 6 times b. And the second component of our vector will be -3 times a plus 0 times b. So we have that the vector 3a minus 6b and -3a is equal to the vector -3a, -3b. And we can find a relationship between a and b by looking at either our top component or our bottom component. In the top component, we have 3a minus 6b is equal to -3a. If we subtract 3a from both sides and divide by -6, we will get the relationship that 3a minus 6b is equal to -3a, so a is equal to b. Notice that if we had used the bottom components, we would have had -3a equals -3b, and also found the same relationship that a equals b. This happens due to the fact that any constant multiple of an eigenvector is also an eigenvector. So we will only have one relationship between a and b. If we got a different relationship between a and b from both components, then when we solve for a and b, there would only be one vector. But we want infinitely many vectors, so there can only be one relationship. Because of this, we only have to look in the top component or the bottom component. Now that we have this relationship between a and b, we need to pick an eigenvector. It can be any vector so that a equals b, other than the 0 vector, which by definition cannot be an eigenvector. To make things simple, let's take the vector 1, 1, though we could have just as easily taken 2, 2 or 3, 3. Now, moving on to our other eigenvalue, lambda 2 equals 6, again we need an eigenvector v2 equal to some unknown values a and b, so that the matrix A times AB is equal to our eigenvalue 6 times AB. Again, we need to multiply out both sides. On the right-hand side, we'll have 6a, 6b, while on the left-hand side, we'll have the same matrix multiplication that we had above, 3a minus 6b up top, and -3a down bottom. So looking at the top component here, 3a minus 6b must be equal to 6a, so we get the relationship between a and b that 3a minus 6b is equal to 6a. And now, subtracting 3a from both sides, we get -6b is equal to 3a, and when we divide by 3, we'll have that a equals -2b. Again, we just need to pick any values a and b that satisfy this. If we pick b to be 1, then we'll have a as negative 2. And we'll get the vector negative 2, 1 as our eigenvector. And from here, now that we know our eigenvalues are negative 3 and 6, with associated eigenvectors 1, 1 and negative 2, 1, we can build a general solution. Y of t equals c1 e to the negative 3t times 1, 1 plus c2 e to the 6t times negative 2, 1.